Oh, by the way, I was talking to yeah, trying to organize a group where we start. Nice. Because the guys are talking on the mic because they are recording I think. Good. Hello, everybody. Good morning. So it's really a pleasure and honor to introduce Professor Faruk Gul from Princeton University. Professor Gul is one of the leading economic theorists of his generation. His research has made fundamental contribution to game theory, decision theory, auction theory, and consumer choice. His work on temptation, self-control, random expected utility, and durable goods monopoly has had a lasting impact on modern economics. Please welcome Professor Faruk Gul.
Thank you. It's a great pleasure to be here. This is joint work with my friend and colleague Wolfgang Pressendorfer. So let me tell you what we do. No, let me say one thing. So I won't be presenting a particular statistic model. My goal here, our goal here is to give it look at statisticians and statistics in a sort of to identify some common elements and features. Hopefully that will raise a couple of questions, maybe suggest why certain types of formulas appear all the time, get you to maybe ask questions like, why are there statistical models to begin with, etc. What are the roles of these things? So it's really not about statistics, but more about statisticians. So let me tell you how we organize what statisticians do. So we're going to, the sort of many statisticians engage in sort of fairly standard activities. They estimate, they make predictions, they suggest possible causes for an observation, address concrete questions. So these are like when there's a statistician working with a group of doctors on a paper in sort of clinical research. In the US, football teams have statisticians as advisors. They call them numbers guys. So this is the kind of routine things, activities that we have in mind when we talk about type 1 activities. So things like, does a new drug produce better outcomes than the existing treatment? Did the increase in fines lower the rate of violations? Did the price increase reduce revenue? Sort of standard measuring questions. In contrast, most of the statisticians or econometricians we encounter do other kinds of stuff. They do things like they develop arguments favoring one method over another. They provide justification for using a particular estimator. They prove limit theorems. They offer higher level arguments about how methods should be analyzed and criticized. So it's somewhat different than the routine activities of statisticians. We're going to be doing that kind of stuff. So we're going to be looking at statisticians. and with the goal of analyzing the sort of more standard activities. What do they involve? What are common features of them? So let me tell you what I think are the two biggest differences, well, biggest surprises, I guess you might have. One of them is we're not going to talk about randomness. There's going to be no stochastic processes, no convergence, etc. The second and more difficult issue is we're going to take what we call an a priori approach and cardinal preferences. So a priori approach means, you know, in much of statistics, you assume that some data has showed up, and now we have to estimate. And so we can, well, I will explain what that means. So let me try to explain what these two things. So here's the description of the no randomness part. We're going to model a statistician as two preferences. One of these preferences we're going to call the estimation preference, and the other one is going to be called the prediction preference. So instead of asking questions like what stochastic process generates these data and how can its parameters be estimated, which would be the standard way, we say, how does changing the input data affect the statistician's prediction? So this is the kind of question we're going to ask. So we're trying to shift things to the language of preferences. Okay. So why are we doing that? Well, many statistical methods posit unobservable parameters or hyperparameters, and we don't want to. Bayesian methods also require conventions for choosing a prior. We instead describe the statistician's observable in quotes, comparative judgments. Okay, now here's what we mean by the a priori approach. An ordinary or ordinal preference might say that model M fits data D at least as well as model M star. So that's the kind of statement you make, right? The M star is a better fit than this. In a cardinal statement, we make a statement, we're a little bit more ambitious. We say things like, given data D, the improvement from model M2 to M1 is bigger than the improvement from M2 star to M1 star. So we're allowing these kinds of comparisons. So this is what we mean by a cardinal preference. And let me describe what we mean by a priori approach. So we can say, standard would be to say something like model D, data D and model M combination is a better fit than data D and model M star combination. So you would start with a given data set and you would compare models. In the a priori approach, we also we allow ex ante comparisons. So things like, does a model D, how does the fit of data D and model M compare to the fit between data D star and model M star? Notice that I didn't insist on the model being the same. Again, this is a richer set of comparisons. Why are we doing that? Well, we need to do it. How come we can do that? Well, we have two excuses. One of them is, if you look at most statistical analysis, there's a loss function, and that enables you to do these things anyway. You can just take that at face value and allow yourself these comparisons. And anyway, expanding the set of comparisons is what decision theory is all about. That's what we do in decision theory. So that's the whole name of the game. All right, that's a mild apology. So how reasonable are these things? Well, I think one is relatively easy to defend. The idea of just, not talking to random processes, but what kind of predictions you're making given what kind of input data is a perfectly sensible way of looking at things. The second one is a little tougher. So this insisting on a priori comparisons and insisting on comparing improvements, changes rather than absolute values. So making cardinal preference versus just ordinal. Those are heavier burdens. And in particular, if you were a hardcore revealed preference person, it would be difficult to defend these things, because you can't force a statistician to make these choices because he either has one data or the other data. All right. Is the whole thing worth it? Well, you'll see, and you can decide in a few minutes. So let me just go on with my story. Okay. So to get a cardinal preference, it turns out there are two key properties. One of them is the reversal property. It says if xy is better than wz, then zw must be better than yx. What does this mean? This means that these changes have a sign. So if you think moving from y to x is better than from z to w, then it must mean that when you multiply the whole thing by -1, the inequality is reversed. So, right? So this is an obvious property that would have to be satisfied. If you interpret this preference as an inequality, this is exactly saying switch things from one side of the equation to the other. Okay, so that's the reversal property. The second property is the exchange property. It says if moving from z to w, y to x is better than moving from z to w, then I can swap y, the place of y and w, and still preserve the ranking. Again, that's what, if you think of this as an inequality, this is just saying if you move w to this side and y to this side, the inequality is preserved. Okay, so these are going to turn out to be two key properties. This is choice theory, so we're going to assume continuity as needed. Okay, we're going to assume continuity as needed. All right. So a binary relation, I want to say, hopefully I won't mess things. I want to say this carefully. A binary relation on x to the power 4 has a measure of fit representation if this happens. Xy is better than wz if and only if f of x minus f of y is less than f of w minus f of z. So this is a difference representation, but now less is better, right? Lower values mean better. And we're calling it a measure of fit, and we're making less is better because we want to match statistical preference, right? In statistics, you often don't talk about utility functions, but you talk about loss functions. So things, the bigger the values, the worse things are. So the first theorem is every continuous cardinal preference relation on a compact metric space has a measure of fit representation. So what's the substance of this? It says, look, basically you can guarantee an additive separable representation of the differences if you have the two properties, exchange and reversal. Okay? This is closely related to the middle theorem of a very old paper by Debreu. It is not well known because its motivation is a little unclear, which I don't want to explain now. And it's bracketed by two very famous theorems. So this one is in the middle, so it doesn't quite get the attention. The main difference between what we do and what's there is in Debreu's setting, he's talking about probabilities. So for that reason, the reversal property comes for free. Okay, so the reversal property is built in, so we actually have to assume it. It's closely related to his theorem. All right, so that's the tool. Okay, so we're borrowing essentially a tool from Debreu, and now we're going to do our little bit of statistics analysis instead. So here's what I've been talking. We're going to have an estimation preference and a prediction preference. D is the set of all data. It's very abstract, bless you. M is the set of models. We don't know anything about them so far. We're going to use ABCD type letters to denote data, ML kind of letters to denote models. This is the estimation preference mu, and preference pi is the prediction preference. So this one describes what the statistician does when estimating a model. This one describes what the statistician does when making predictions. All right. Just want to remind you, a cardinal preference. So the first estimation preference says the move from D2 M2 to D1 M1 is a bigger improvement than the move from D4 M4 to D3 M3, right? So when you're estimating, you're going to think that the match between the improvement in match between the 2s to 1s is bigger than the improvement in match from 4s to 3s. And a similar statement for making predictions. Okay, a similar statement for making predictions. Okay. Both of these are cardinal preferences. And we're going to say that the two cardinal preferences are consistent if there's a level of agreement between them. So what's the level of agreement? It says, look, if you pick the same model on one side of the preference and the same, and possibly different, but the same model in the comparisons on the other side, they agree. Okay, so in general, if all the M's and all the L's are arbitrary, they may not agree. But if you're comparing improvements in one fixed model to an improvements in another fixed model, the two preferences agree. Okay, that's what we mean by consistency. So you can't be doing totally unrelated things when you're estimating versus when you're predicting. Okay? And we're going to call this pair a statistical theory if it has these two consistent cardinal preferences. All right. Now, I want to make a simple observation. If you have a cardinal preference, you can clearly derive an ordinal preference from it, right? If the improvement from y to x is better than the improvement from x to y, it must mean that x is better than y. What else could it mean? So that's a definition over there. So that's the ordinary preference implied by a cardinal preference, okay? I'm going to use that to simplify three non-degeneracy conditions. One of them is to say there are no vacuous models. So it can't be that for any model, every data fits equally well, right? So for any model, you can find 2 bits of data such that it does better with respect to one piece than the other. Similarly, there is no completely uninformative data. There's no null data. So what does that mean? For any data, you can find models such that one model fits the data better than the other. And finally, models aren't dominated. That there are no, whenever I have 2 different models, I can find one data that fits it better as a prediction, fits one better than the other as a prediction, and another data that fits one better than the other as an estimation, when I'm estimating. Okay, so these are really non-degenerate. There's no domination. There's no constants, right? There's no. So these are non-degeneracy conditions. So let me give you my first theorem. There aren't that many. So we're gonna say that 2 functions represent a statistical theory if one represents the prediction preference in a cardinal way and the other one represents the estimation preference in a cardinal way. And the theorem says every continuous non-degenerate statistical theory admits a continuous representation with this property, so that the estimation prediction estimating measure of fit is equal to the prediction measure of fit plus a term that only depends on the model and not the data. And at this stage, you're supposed to say, that seems vaguely familiar, right? So a lot of statistical models have this, a lot of statistical theories have this feature. Okay, So how do we interpret this? We're saying estimation and prediction use the same fit criterion, but there's a model-specific penalty that doesn't depend on data when you're estimating. Okay. So if you want, for example, to estimate something, you ask yourself, what's the best model given this data? And then you would say, well, let me minimize this overall possible M. So that's the best model for this data. And then once you decide what your data is, you can say, well, what should I predict? Then you minimize it. So you find the data that fits this best given your model, but not ignoring this. Do you see what I mean? So let me say that again because I muffed it. So let me try that again. Suppose you're estimating, you have input data and you want to find the best model. Then you would minimize this and find the model that minimizes this. Now you've decided that you have your best model, and I ask you, what do you think is going to happen in the future? You would plug the model that you've estimated and minimize. Or if I ask you which which outcome is more likely, you would use just this with your estimated model. Okay? So that's our notion of a statistical theory. And then we're going to do a little normalization. I don't want to say too much about that. That's why these parts are here. We want some kind of uniqueness theorem, and we also want the p term to be at most normalize it so that it's 0, and we want it to drop out because we want to interpret the m that minimizes the p term as the prior, as the key variable in many of these statistical models. So this is just normalization, and these follow from the non-degeneracy assumptions. So what do I want to say? We're looking for a representation. We're going to require that P, by adding a sufficiently large constant, if you like, we're going to require that P is never negative. And we're going to, nothing is constant. And then for the last one, I don't want to even say it. It's the non-domination, no domination requirement stated in the representation. So we're going to write a statistical theory like this: the estimation preference phi plus p, and the prediction preference just phi represented by phi. Okay, and if p is not constant, then the m that makes the p 0, we're going to call the prior. Right, and you can see that that's going to match a lot of actual models very well. So if the p is not constant, that means there is an actual penalty for certain models as opposed to others. Then the one that assigns the lowest penalty, we're going to call the prior. Okay. Now let me show you what fits this. There's a little uniqueness. Every continuous non-degenerate statistical theory has a proper representation. A proper representation is unique up to a common positive affine transformation. So, all right, here are some examples. For these examples, we want to think of the data set the way you would think of the data set in a standard econometrics course. X is the n vector, n times k vector of input variables, so matrix of input variables. Y is the endogenous variables, realization of the endogenous variables. T throw of X contains the k explanatory values at time t, right? This is the sort of standard setup. In many of these examples, D and M are not going to be compact. I want you to give me a pass on that. This particular theorem, theorem 1, we could generalize to non-compact sets. All that's really needed is connectedness and separability, and we're even going to get rid of connectedness in the future. All right. So least squares regression. The phi, so a model is a vector of coefficients, right? And data is a matching is the matrix of realizations of the endogenous variable. And this is the least sum of squares, right? And in classical least squares regression, it's the same model either way. You use the same preference for estimation and prediction, so P is a constant 0. All right. In lasso or ridge regression, the phi is the same. It's still the least squares. And then the penalty term is either an absolute difference term from some fixed beta, or again, a square difference term from beta. And the P is 0 if and only if the vector is 0. So the preferred model, the model that one might be inclined to call the prior, is all parameters having 0, 0. And, if you look at a statistics text, sort of what level of statistics, sort of third-year statistics course kind of thing, or fourth-year statistics course, there'll be some discussion about, oh, look how the lasso regression is a lot like how, this term, the penalty term, is a lot like the prior, plays the same roles as the prior. Well, I guess what we want to say is, of course, you have the same objective as you did with the prior. This is I will describe what that is in a little while. But okay, so that's the lasso and ridge regression. The third example I want to mention is variational inference or elbow estimation, empirical lower bound. So here, there are a couple of common parameters that I need to talk about. First, the Z is a set of parameters of your model. They could be various things. And you have a likelihood function of getting the various data given the particular model. Not model, I want to save the model for my term, given the particular parameters. And the phi is negative of the expectations of log likelihoods. And a model is here, it's a distribution over parameters. Okay, so it's a distribution over z's. So every z gives you a likelihood function about which data could appear, and a model in this to make this fit our model, our theory, you have to interpret a model as a probability distribution over these z's, the parameters. Okay, then phi is this exactly. It's the negative of the expected log likelihoods, and the penalty is the KL divergence. Okay, so how is this used in statistics? Well, the main uses is sometimes computing posteriors is difficult. So one wants a notion to sort of come up with an estimate of the posterior and have a sense as to how far off this could be. So in actual applications, it is important to consider situations where the posterior distributions on the parameters is not within the set of parameters being of models being considered. So you do the best you can within the restricted set of models that you're allowed. However, if the exact posterior belongs to M, it is the best model that fits the data. So when you minimize this term, given data across all models, you get exactly the posterior distribution on the parameters. Okay, that's what the KL divergence does for you. All right. These are my examples. There's a proposition coming up, but it's a very modest proposition. I don't want to pretend that there's a big result here. What am I trying to convince you? I'm trying to convince you that this phi equal this formula, this phi mu equals phi plus p fits a lot of things. That's really what I want to convince you of. So here's another thing that fits. So I would say, what is a hypothesis test? Well, I want to say a hypothesis test is a way of getting a model with a prior from a model that doesn't have a prior. So take a standard classical model. So P is constant 0. So it's phi comma phi. Both the estimation preference and the prediction preference is phi. And now we're going to add a null hypothesis. What does the null hypothesis say? It says I'm going to pick a favorite model, nu, and if any model doesn't improve on that by at least tau, then I'm going to reject it. If it improves by tau, then I'm going to reject the null hypothesis. Well, that fits our framework if your penalty function is exactly this. If m is equal to nu, no penalty is 0. For any other m, the penalty is tau, right? That makes the story fit. So proposition 1 says a model of this sort is a hypothesis test if and only if p takes on exactly 2 values and there's a unique prior. Okay, so the hypothesis test fits this framework too. Okay, now we're going to shift gears just a little bit, and we're going to talk about something else. So something closely related. Don't get me wrong, I made that. So I want to say, look, you never get to observe a model. Right? Model is not it's something you like to talk about, and what I'm going to argue is it's something that organizes how you want to relate input data, simplifies the task of relating input data to output data, but it's neither observable and logically neither necessary. Okay, I know in statistics you talk as if there's this, it's this unseen thing that somehow coughs up data, etc. But I don't want to think about it that way. It's just a tool to describe the statistician's preferences. Okay. So the only thing you ever see is you see the statistician collecting data, and maybe you see him, if you're outside of academia, making predictions, and that's that. Okay. So it must be reasonable, especially if you do choice theory, to ask, well, what does this relationship between input data and output data look like if you aggregate, if you integrate out the models? Again, if you look at demand theory and stuff, this is a very, very common question. So the question is, how can estimation and prediction be combined into a single cardinal preference over input data, output data pairs? And of course, the reverse question, which cardinal preference over input data, output data pairs can be interpreted as the empirical description of a statistic theory? The answer to the first question is exactly is too strong. A lot like deriving demand from preferences, from utility functions. And the answer to the second question is a bit like Afriot's theorem, where you say, look, here's a function that looks like a demand function. Does this come from a real utility maximization problem or not? And that's what we're going to do. So that's going to be the last thing we're going to do. Okay. So now, what is the object that we're getting? We're going to get a cardinal preference that fits between data pairs. So is the improvement in fit between D1 C1 from D2 C2 to D1 C1 bigger than the improvement from D4 C4 to D3 C3? That's the kind of question. It's always cardinal, right? It's always cardinal. So how would you do this? How would you figure out how to eliminate the model stage, given the analogy that I'm pushing between demand theory and this? Well, you would say, choose a model that fits the input data the best, then ask yourself, how well does this prediction work given the best model from the input data, right? That's exactly the analog of computing demand. So you get so how well do D and C fit? Well, you take D and you find the best model for it, because that's what you're going to go with. And then, given that model, you're going to ask yourself, how well does C fit? Okay. So that's it. That's really the sort of the demand maximizing type exercise. So a continuous function phi e is an empirical description for the statistical theory, that one, if there's a function such that blah. Before trying to explain this, I want to say I cheated. If I wasn't scared about making this slide even more crowded, I wouldn't say it's an empirical description. I would say it's the measure of fit for the empirical description. But you understand. Okay, so I'm going to say this is an empirical description for some statistical theory if, given data D, M star D is the best estimate of the model. That's what the first line says, right? It does better than any other model, weakly better than any other model. And this works for every D. So M star of D is a selection from the optimal models for each D. Okay? And then my prediction, my assessment of the fit between D1 and C1 is exactly the how good a prediction C1 is given the best model from D1. Does that make sense? So first I get the data and I use the best model. And then to model the fit between that data and this possible prediction, I say, how well is this prediction given that model? Okay, and that's it. So that's how I derive the optimal model and how I derive the best fit given the model. Let me say this one more. Okay. So notice what's happening here. The fit between input data and output data is exactly the fit between output data and the best model given the input data. That's all I want to say. That's exactly what we're doing. No, that's my next theorem. So that's exactly you need one condition. You need one condition. Okay, good. That's a great question. So candidate empirical descriptions cycle. So I'm going to take a continuous function from D cross D to R, and I'm going to call that a candidate empirical description. And I'm going to ask myself, when is a candidate empirical description an actual empirical description given some statistical model? And this is exactly like Afriad's theorem, right? You write a function that says, here's how much I demand of each good given these prices, and you ask yourself, is there a concave utility function such that when you maximize, you get that demand? Okay. So we're going to call a finite sequence D1 through Dn a cycle if it happens that the sum of phi e D1, D2, D2, D3, D3, D4, D4, D1 is less than the sum of congruent pairs. So you do better by mismatching, creating a cycle of mismatches than you would by perfect matches. So that we're going to call a cycle, and we're summing up. See, that's the beauty of having cardinal things. You can sum things up without being embarrassed about it. It all makes sense. You could always easily translate these into preference statements. And the inequality says, okay, a Camber empirical description is justified if it is an empirical description of some statistical. So this is like saying the Afriad test is passed, okay? And what is the theorem going to say? It's going to say a candidate empirical description is justified if and only if it has no cycles. Okay, if there is no such cycles, then the candidate empirical description is in fact an empirical description of some statistical theory. Okay, the one thing I want to highlight here is there is no set of models here, right? Because they've already been eliminated. So we have to come up with a trick that says, look, here's a canonical set collection of models. Let me do one time check. Perfect. So I have just enough time. And this, because this is kind of the main step, there are two issues in proving this. The one of them is the step that I'm going to show you. The second one is to move from the case of finite D to a compact, connected, separable, compact, connected D. That step is sort of typical arguments, find a dense subset and a countable dense subset, take limits, etc. So I don't want to show you that, but I do want to. I wonder how are we going to. I do want to show you the first step. Okay, so to show you the first step, let's assume that D is finite for now. Like I said, the rest is usual stuff. And that we want to find a set of models, a way of selecting a model for each data such that the model I select for each data is the best fit when I'm estimating. And then I want the best, the predictions to be ranked according to how I want the prediction that this theory that I'm constructing makes to be exactly match the input data, output data value when I use the best model for the input and look at the prediction fit for the output. Okay, so I want this to happen. Well, there are two issues here. One of them is just obvious. So phi of D, okay, no, it's not that obvious. So let me say one more thing that has to be said. Let me make a bold guess and assume that I can identify the set of models with the set of input data so that the best data, the best model for any given D is D itself. So I'm labeling the models. I'm giving you each model the name of the data that it fits best when I'm estimating. Okay, then this condition says this is what I mean. This is what it means for it to be an optimal selection. The best model for data D is D itself. Once I've done that, then the second requirement says, look, the fit between input data C and output data D has to be exactly the fit between model D and prediction C, because I've also identified them with the label. So this one is done. So all I need is to find a P that satisfies that equation, right? If I could find a P that satisfies this equation, I'm done. For every value, this has to hold. Can I do that? Well, let's do a couple of tricks. Multiply the equation by so that it's, we're going to maximize. So multiply it by -1 so that instead of minimizing, we need to maximize. If negative values scare you when you're talking about utilities, add a big constant. Okay, and now interpret phi EDC as a utility function. So for each model, there's one person for each data, there's one person whose name is exactly that data. And for each, and possible consumptions are also the data. So there are as many people as data sets and as many goods as data sets. This is starting to look like an assignment problem, right? This is starting to look like a unit demand economy. And what's going to happen for the unit demand economy is that the no cycle condition is going to say that it's efficient, maximizes sum of utilities for each person D to consume data D. Okay? But if that's the case, that means, for assignment problems, that efficiency and equilibrium are the same. So there must be shadow prices. There must be prices that support that allocation, that efficient allocation. And then what does that mean? Well, that means the question at the top is that. So finding the wall-raising prices of this imaginary economy is exactly what I needed to do for this. And then the rest is, you know, find a sequence of finite economies, it converges, use some more properties of these economies to generate a sequence of increasing prices to ensure that they converge, and then a little continuity stuff. Okay. All right, back to theorem. So here are my conclusions. Okay, here are my conclusions. One, we wanted to facilitate discussion of statistical theories without invoking properties of abstract observable objects. Are the error terms correlated or independent? Do the hyperparameters have a joint normal distribution? I don't know. But consistency implies this, and I think this is what the statisticians want. You know, this formula is really all that elegant talk is really, I think, to derive this function. So whether they talk about classical statistics with a penalty term, lasso, ridge, whatever, it always seems to be that they want something that looks like this. Familiar methods correspond to different penalty functions. Okay, so that's what I mean by our goal is not to do statistics, but to identify common things. All the action is, of course, is in which, you know, they know which penalty functions work well in which situations. That's something that I'm not commenting on. We're just trying to organize describe the activity. So the penalty functions combine empirical evidence with reasonable prejudice, right? So that's apparently it's not good enough to predict that the future is going to be just like the past. You always want to interject a little bit of this prejudice, and you can call the prejudice the prior, the null hypothesis, regularization target, as many names as you want, but that's what it is. It's a prejudice. It's saying, I'm guessing certain models are better ex ante than others, and I'm going to penalize you if you want to pull the data too much away from my preferred models. And the last little bit is observable empirical descriptions are rationalizable exactly when there are no cycles. So that no cycle condition is exactly what you need. Of course, for statisticians, the models have a way more important role because the checking whether a cycle has an arbitrary data or arbitrary length of data is impossible. So it's a more efficient algorithm is to postulate a set of models and start from there rather than look.
But if you can test that, it can be important, right?
Yes. Yeah. Hopefully. Thank you. Very sorry. I understand. So you're interpreting behavioral as a sort of a description of possible departure for rational. I'm interpreting as behavior of the statistician. Okay, so, but I see what.
Another one. So one of the roles of model is determining what kind of data is going to be important or informative. And that's, you're taking the data that you're given. Another part of what statisticians do, try and figure out what they need to look at. Is there any way to...
Yes, I see what you mean. Yes, I'm sort of coming in after that issue has been resolved, but I totally understand. I mean, that is a, you know, so that's part of the theory generating process, etc. But I'm assuming all that's been done and I'm coming after.
Okay, thank you.
Excuse me, if we just like to make an announcement that if you're a student who is eligible for a refund for the hotel or flight and have not yet collected the refund, we recommend you do that as soon as possible. Thank you.